And I'm very happy to welcome Grégory Schehr from Sorbonne, I guess, most likely.
Yeah, that's true.
Who's together with Jeremy Boutier are going to talk about non-interacting trapped fermions at finite temperature. Thank you very much.
Okay, thank you very much. Thank you to all guys, and in particular, thank you, Dan, for the organization of this meeting. So I'm very glad to give this first lecture of the two of them. Second one will be given by Jeremy on Thursday, and this has to do indeed with non-interacting trapped fermions at finite temperature. So as you may know, I mean, I'm actually a physicist, and I started to work on that mainly with motivations from physics, both from the theory point of view, basically in the context of quantum many-body systems. That means trying to understand the collective effects that arise from quantum effects, and in particular in the context of fermions, which is the topic of these talks, of these lectures. The main ingredient is what is called the Pauli exclusion principle, which essentially forbids fermions, fermionic particles like electrons, for instance. This Pauli exclusion principle forbids them to essentially occupy the same quantum state. And we will see that even though we are looking at non-interacting particles, this Pauli exclusion principle eventually creates a kind of effective interactions, repulsive one, which turns out to lead to some quite nice and interesting effects. Now, another motivation from the theoretical point of view is that, and this, I guess you know this very well, is that fermions turned out to be connected to many other models, either in physics, in statistical mechanics, but also in mathematics, ranging from probability to combinatorics and many other integrability and so on. So that makes the subject quite rich and quite lively, and that's why we were interested to work in this subject. Now, of course, among the connections with both math and physics, there is one which is quite important and which I will come back to in a minute, which is the relation to random matrices, and that will be somehow one of the core of the point today. Now, this is from the theoretical point of view, and although I'm a theoretician, I'm also interested in some aspects related to experiments, and that's quite motivating in the sense that nowadays people are able to build these quantum Fermi microscopes, which basically allow them to really observe quantum particles, namely fermions. So they are basically able. So you see here. This is something, I mean, from experiments, some two-dimensional experiments from the group of Marcus Greiner at Harvard, where they are really able to take picture of the Fermi gas. So these are each bit, I mean, each point here, each pixel here corresponds to one atom. And then the natural question is what can be said about the statistics of the collections of these points, okay? And that's, that has indeed important consequences, physical consequences, and that's actually part of the motivation for this work today. So I decided basically to divide this first lecture in three parts. So I will first start with the first model to start with, I think, because it gives already the insight on how this problem is connected to random matrices, and we will see how the connection is actually quite straightforward and direct in this case, in the case of fermions in a harmonic potential at zero temperature. So I will start with the simplest case of zero temperature, exhibiting this connection to RMT, and then I will go to finite temperature. Basically, I will try to explain how one has to go from basically what is called the canonical ensemble to the grand canonical ensemble, and that's somehow the main step. And once we are here, I will show you how one can derive some nice asymptotic limit of the kernels that we will have obtained. And in doing so, I hope to arrive at this connection to the KPZ, to the Kardar-Parisi-Zhang equation, or more generally Kardar-Parisi-Zhang universality class. And that will be more or less what I would like to talk to. So let's move on, and let's take this first item. So basically here today, I will mainly talk about fermions, which are on continuum space. Okay, so there is no time here; there is only space, but they live in a continuum space, and that will be somewhat probably quite different from the perspective that you will get from Jeremy. But basically, I will just consider here n fermions without interaction. Okay, and so that means again only exclusion. That's what I'm saying. And the point here, of course, is that they are living in a potential V of x. Okay, so that means that typically I would have such a situation where basically I will consider such fermions in a trap okay, as a function of x. And typically today I will discuss the case where I simply have a harmonic potential 1/2 of x squared. Okay, so that means that in terms of quantum mechanics, that means that I have a problem where I have a Hamiltonian which is my operator basically, which is just the sum of one particle operator okay, and this H here is just a single particle operator. Okay, so in this case, this is just p squared over 2m plus v of x, and that means this in this case, okay, 1/2. Okay, let me just put the mass equals to 1. I think you won't be too unhappy with that. Okay, so that's our model. Okay, now to start with, what you do in quantum mechanics is that you need to start with one particle eigenfunctions, which are basically the eigenfunctions of this operator. Okay, and I will denote them by phi k of x. And in this case, this phi k of x, you can construct it explicitly in terms of Hermite polynomials. Okay. So k here is an integer that starts at 1, and it's proportional to exponential of minus x squared over 2 times h of k minus 1 of x, with k equals to 1, 2, etc. And this guy is just the Hermite polynomials. Okay, and the epsilon k associated to that, so that means the eigenenergy, which we'll not use so much here, but still is just, in this case, is just say half, so k plus half. Sorry, k minus half. Okay, so these are the building blocks. These are the building blocks, and from them, I will be able to say essentially what happens at 0 temperature when I consider n fermions experiencing only the Pauli exclusion principle. Okay, so let's look at what happens at t equals 0. And what I want to construct is the ground state of the system. So up to now, somehow I did not specify what is the nature of the particles, because I was just considering somehow single particle. But I want just to consider the ground state of n fermions. And because of the Pauli exclusion principle, this ground state wave function has to be completely anti-symmetric under the permutation or the exchange of any of two particles. So that means that if I call now psi 0, so let me now construct the eigenfunctions of the full Hamiltonian H, capital H, which will be, say, E0 psi 0. Now the psi 0, because it has to be a solution of this equation and of the Schrödinger equation, and also because it has to be completely anti-symmetric, then it's built from the single particle wave function by constructing what is called a Slater determinant. So this is just a simple normalization, but now comes the determinant. So I will just denote in this way. Okay, so that's our guy. And this is what is usually called a Slater determinant. Okay. Now note that in principle you could construct a Slater determinant with any of the eigenstates, but here, because I'm considering the ground state, I'm just considering the first level. Okay. So in other words, if you remember what I was drawing there, basically you need to understand that you have all your states here. So this is k equals 1, say. Then you have another states which is k equals 2. Then k equals 3, etc. Now, what happens when you put fermions is that because of the exclusion principle, you can put only one fermions per level. So you will fill the first level if you have one fermions, and if you put the second fermions on the second level, the third fermions on the third level, etc. And eventually, the last fermion will be on the level k equals n. Okay. So that's really the way you would construct your wave function. But in principle, and that's the situation that will occur at higher temperature. In principle, if you're at higher temperature, you could actually have states which say above this guy, and in principle, you could construct any Slater determinants built out of any sets of n excited states of your fermions. But for the ground state, it's clear that because you have to minimize the energy, this is the only way you can fill up these levels. Okay, so that's our guy. Now, if you just inject the expressions of the phi k's, which are given here, if you take these guys and if you inject this one in the determinants, well, you will see that well, first the Gaussian term here that will simply factor out, and on top of that, you can then manipulate a little bit the determinant of this Hermite polynomial. And if you start to manipulate it, what you will end up with is a simple van der Monde determinant. So this is a manipulation that I guess many of you have seen in RMT. This is quite standard, but let me just write what I said, quite quickly, so that we understand what we are doing. So what I'm saying is that this guy, this psi 0, you can just, as I said, factor out the Gaussian terms, and then you are left with the determinant of these Hermite polynomials. Now again, what I said is that if you start to manipulate or make linear combination of rows or columns of this determinant, this is a standard exercise in linear algebra. What you will find out is that this is just proportional to the product, say for I less than j, xi minus xj. Okay. So that's already very similar to what is known in random matrices, right? So if you look at this eigenfunction now, this is just basically the product of Gaussians times van der Monde determinant. And quantum mechanics, the physical observable, the physical quantity is not psi naught directly, but it's the modular square of psi naught. So here in this case, everything is real. So this is just psi naught 0 squared. And that's the joint PDF. It's the joint probability density function for the positions of the fermions. And this is given by psi 0 squared. Okay, so that's the interpretation that quantum mechanics gives us. So it's a joint probability density functions of the positions of the fermions. So again, here the randomness comes completely from quantum mechanics, from quantum fluctuations. There is no temperature. And this is given by psi 0 squared. Modulo squared. And so here, if I just take the square of this term, then what you get is an expression which is quite familiar, because up to some normalization, this is a PDF, so it has to be normalized. This is just exponential of minus the sum of xi squared times the product y less than j xi minus j squared. Okay, so that means that
is this a joint PDF for the ground state, right?
Yeah, absolutely.
So somehow random matrix theory doesn't usually touch on excited states joint PDFs,
absolutely.
right?
Yeah, I will come back to this maybe if I have time, but in the sense that we will see that it's actually possible to construct matrix models which actually mimic or correspond to the joint PDF at finite temperature, but these are not the standard and classical models. So the standard model and the classical model that we know here, I'm talking about GUE, which corresponds to a case where you don't have any interactions, but in general, G beta E would correspond to the ground state of a fermionic system in presence of a certain type of effective interactions on top of the exclusion principle. But so the classical model indeed corresponds really to T equals 0. So that means that they really take into account only purely the quantum fluctuations. That's what I mean. Is that clear?
Yes, thank you very much.
Okay. So as we said, this is indeed the connection to GUE. So basically, I mean, I guess that most of you or every one of you is familiar with the Gaussian unitary ensemble, but essentially what I want to say, and maybe I just write it here, is that we have here a direct mapping to GUE. Okay, I guess everyone knows what the Gaussian unitary ensemble is. So what is quite interesting here is that, as we know, GUE, say for beta equals 2, then is actually a determinantal point process. So that's very important. And so that means that the xi's in particular, the xi's form determinantal point process. Well, in fact, determinantal point processes were essentially introduced by Mackey precisely to describe fermions. Okay, so that's what I would like to call DPP. And again, that means that the central object that we have from a determinantal point process is the kernel. Okay, and this kernel, I will just call it usually Kn of X and Y, and that's just the standard. So in our case here, this is just the sum for K equals 1 to N of phi K of X In general, that would be phi k star of x, phi k of y. Now, this is actually true for any quantum system at 0 temperature. So in general, this phi k's turns out to be only the eigenfunctions of the Schrödinger operator. In our case, they are quite simple because this is just the standard kernel of GUE. Okay, so this is the Hermite kernel, if you want, in this case, and you can even simplify it using Christoffel-Darboux because you have orthogonal polynomials and so on and so forth. I will not enter into these details, but at that point, you see that you can essentially use everything that you know from RMT to study your fermions, and that actually allows to study many things that people had not really studied in the context of fermions, in particular the fluctuations at the edge, and that's something that I want to say in a minute. I'll come back to in a minute. So in particular, what it means when you have such a DPP, is that you can construct the correlation function very easily as a determinant of involving this Kn. Okay, so that means that you have all of your endpoint correlation function. Then it's just okay, I denoted my Rn, x1, xn, so it's basically constructed by integrated your full measure on the capital N minus small n remaining variables. And as you know, this can just be written as the determinant of the kernel. Okay, so I guess that you are all familiar with that. So I guess it's probably not really useful to enter into more details at this stage, except if there were questions, of course. Okay. Now, in particular, there is the first correlation function that we can get is just the density, right? So in particular for n equals 1, this is just the density. And the density in this case is just usually what we call rho of x. And in the context of in the harmonic potential, this is well known. I mean, what we expect is that in the large n limit, this rho of x will eventually converge to the Wigner semicircle. Okay, so that's eventually in the large n limit, we will have something like that. Okay, so okay, this should be the Wigner semicircle. Okay. N goes to infinity, and this is a function of x, and basically the support in the large n limit. I mean, in the unit that in the natural limit in the natural scaling that arises for fermions, this is just this guy. Okay, so the edges are just that minus square root of 2n plus square root of 2n. Okay, nice. Now, because we have a determinantal structure, there are many things that we can compute. And for instance, one thing that I would like to discuss a bit late, in a minute, is what is called the hole probability. So what's the probability to have a certain hole in space? So that means what's the probability, for instance, say to have a hole on this segment here, and this can be expressed in terms of Fredholm determinant constructed from the kernel that I just discussed. Okay, so this is I guess well known But in particular, I should say that one thing that people have been interested in, and in particular in the fermions community, and I mean coming from RMT, is really what happens at the edge of the Wigner semicircle. This is connected to the Tracy rhythm fluctuations that you know very well. But in particular, because I mean one quantity that you might be interested in is, as I said, whole probabilities. And a whole probability, for instance, in general, you could ask, okay, what's the probability that, so you define J, which is an interval. So you define, say, J, which is a part of R. So it could be, can imagine that your J would be something here, for instance. And you could ask the question, what's the probability that there is no particle? So if I call Nj the number of particles in J, well, in general, you could be interested in the statistics of Nj, but the simplest quantity that you may look at is what's the probability that Nj is just equal to 0. And this actually can be written as a Fredholm determinant, which is determinant of 1 minus the projector on J times Kn Pj, where basically Pj of x here, I mean, roughly speaking, Pj of x is 1 if x is in J, and 0 if it's not in J. Okay, so it's just a projector on your segment J. And in particular, from this whole probability, you can ask, and I'm just introducing it now because this will be a kind of leitmotif in the following. From the whole probability, you can ask or try to say something about the distribution of the position of the rightmost fermion. Okay, so that's something that I want to discuss a bit. This is just a kind of whole probability, if you want, but I just want to look at the position of the rightmost fermion. Okay, so let me call this guy X max. Of the Xi. And basically, this is what I want to compute. It's a kind of whole probability, which is just the probability that X max is less than M. But this probability is just the probability that you don't have any particle in the interval M plus infinity. Okay. So it's like the probability that the number of particles, say in M plus infinity, is equal to 0. Okay. So that means that this is also a Fredholm determinant. And this is just directly a consequence of the fact that you have a determinantal point process. And this is true for any n in principle, of course. Okay, so I will come back to that. Fine. So these are all the machinery that you have at t equals 0. This is very nice, and this is all exact in the limit, I mean, for any n. And one thing that you would like to understand in what happens in the large n limit. Okay? Now, because I guess you are well familiar with RMT, you know that in the large n limit, basically, we have two scales in this problem. So what we want to understand now is what happens in the limit n goes to infinity. Okay. So, as we know, as I said, if you come back quite quickly to this Wigner semicircle that I was trying to draw before, So you would get this this picture here, and what we know is that there are two scales in the problem. Okay, one is the bulk, so that means if you really look at, so I should recall you that basically the edge is from plus square root of 2n to minus square root of 2n. Now, if you look at what happens far from the edges, so typically in the bulk, well, you see, you can just have an idea of the scale that separates two particles, because you see that you have basically an extension of the total interval, which is of order square root of n, and inside of it you need to put n particles. I have n fermions, so that means that the typical spacing between two particles is just square root of n divided by n, and this is typically 1 over square root of n. So that's what happens in the bulk, indeed. So that's the bulk. That's the first scale. Now, on the other hand, you know that if we approach the edges, either on the right or on the left, it turns out that the density goes to 0, and therefore the interparticle distance tend to be larger. And indeed, what happens is that at the edges, as we know, I mean, we have the so-called Tracy rhythm scaling, where the interparticle distance is actually of the order of n to the power minus 1 over 6, and that's what is called the edge. So we have this quite nice separation of scales, and that means that in both regions, either in the bulk or at the edge, the local correlations, as we know, will be described by different types of kernel. Okay, so essentially, I will not enter into the details, but in the bulk, we have the sine kernel, while if I am at the edge, we have the Airy kernel. And that means that if you scale the things properly around the edge, eventually what will happen is that your kernel Kn will be described by either the sine kernel or, say, here in the Airy kernel, and I just sorry, recall what this Airy kernel is. I will not, and I don't have time, unfortunately, to really enter into all these details, but I suppose that yeah, let me just write it this way in terms of the Airy function. Okay, so that's my guy, and in particular, if you now look at what happens, for instance, for the whole probability, or say that if you look now at the rightmost fermion, and is essentially you replace under a proper scaling, if you replace this Kn by the Airy kernel, this whole probability tends to what is called a Tracy rhythm distribution. Okay, so let me just end up with on that at 0 temperature. So in particular, let's end up with the red color. So in particular, if you look at the cumulative distribution of the rightmost fermions, it turns out that when n goes to infinity, this becomes a scaling function, as we would call it in physics. That becomes a scaling function of this guy, where Wn is just n to the power 1 minus 1/6. Well, in fact, the standard definition is that there is 1 over square root of 2 factor. But anyway, this F2 here is what we call the Tracy rhythm distribution. Just come back to for beta equals 2. So that's the F2. Okay. So that's a nice, that's already nice, because you see that, as you know, I mean, this Tracy rhythm distribution has been studied quite a lot during the last decades, and it has popped up in many problems. Somehow this fermions problem, you see, I mean, it's almost a textbook problem in quantum mechanics, where you see that this Tracy rhythm distribution already arises there. So it's one of the simplest model, if you wish, where one could see this Tracy rhythm, and maybe even in experiments. I mean, people already, of course, I've already observed this Tracy rhythm distribution, for instance, in this nice experiments by Takeuchi on liquid crystals. But here you see, I mean, in principle, one should be able to observe it on this simple free fermions, non-interacting fermions problem. Now, of course, this has to do with what happens at 0 temperature. But in real life, and in particular in experiments, well, we live at a temperature which is non-zero, and it's quite natural to wonder what happens at finite temperature. Okay, so that's what I want to discuss now. And before I move on, I mean, I will be happy to take questions, if any. You can hear me correctly? I mean, everything is more or less fine?
Everything is running smoothly, yeah.
Okay, great.
Please ask questions now or anytime.
Yeah, okay, thanks.
If you have any.
So question is, what happens at finite temperature? Well, we have already mentioned something, which is that, again, if I look at, okay, I'm a bit lazy, I might just come back to this picture, because I think it allows to understand quite well what will happen, is that basically when you are at 0 temperature, you see the ground state is really when you fill up the n first levels. Okay, so these are these n first levels. But as soon as you start to have temperature, well, in principle, you might have the possibility to occupy fermions which are above this latest level. Okay, so that means that you might have excited states where one of the fermions, say for instance, this guy could come here, for instance. Okay, or that guy could come there, etc., etc. So that means that now each of these states that you would be able to construct of, say, n given eigenstates, in principle, you can construct a Slater determinant out of them. Each of these Slater determinants will be a solution of the Schrödinger equation. And in fact, what happens is that all these Slater determinants basically will enter into what is the equivalent of the wave function. So you will have a linear combination of such Slater determinants, and each of them will be weighted by the Boltzmann weight associated to the total energy of the state. Okay, so this is said in word. In quantum mechanics, the good object to look at is just the density matrix, and I will not really enter into the details, but simply give you what should be the starting point. So at finite temperature, in principle, the PDF is more complicated. Okay, let me just call it P joint of x1, x2 of xn. Now, in the language of quantum mechanics, let me just write it this way. And this is just the matrix elements of the density matrix. And what this density matrix is really is just 1 over the partition function Zn times exponential of minus beta inverse temperature times h, which is the full Hamiltonian of the system. So it's
that is not the same. That is not the same beta as the random matrix betas, right?
Yeah. Okay. Yeah. That's a good point. Sorry. Yes. Thank you very much. So beta is just the inverse temperature here. Yeah. It has nothing to. Yeah. Okay. I'm sorry. I'm used beta because I cannot use any other. But that's very important, of course. Now you can check. Well, at this stage it's not completely obvious, but anyway, you can rewrite this quantity here by expanding on the eigenbasis of H, okay, which are all these later determinants, and eventually you can write it. You can have an explicit expression, which I just want to write for you because okay, this is a starting point. So, so in principle, this is just 1 over factorial n Zn. And now here, I will basically sum over all the ordered n uplets, K1, K2, Kn. And for each n uplet, so any combination allows to label any states, any n particle states. And for each of these states, basically, the appropriate wave function, so the appropriate PDF would be the square of a Slater determinant. So this is the Slater determinant that we have seen before, basically. So that would be the phi ki xj. Now I need to take the square because the quantum mechanics tells me that I need to, I mean, the probability density is the modulo square of the wave function. So that's what I'm doing. And now, because I'm working at finite temperature, now each of these determinant square terms now needs to be weighted by the energy. So that's the Boltzmann factor, epsilon K1 plus epsilon Kn. Okay. So that's a bit complicated expression, but it's explicit. Okay. Now Zn, I should define it. Zn is just the partition function. So this is just the trace of exponential of minus beta h. Okay. Now the problem with that, with this model, so 2 comments. The first comment maybe is that, so as you said, it seems that we have lost the connection to a random matrix, at least to the random matrix, the classical random matrix ensembles. That is obviously true. I mean, because now we have a superposition of this determinant square. Nevertheless, there is actually one model. So just a remark here. So there are 2 remarks. The first one is not too bad. Oh, var phi on the right. Yes, sorry. Yes, the notation is not correct. Thank you. This is the, I mean var phi indeed, yes. Is that okay? So this is the phi k's are the single particle eigenfunction of my 1 particle Hamiltonian. Okay, great, Matteo. So first remark is that there is actually a matrix model associated to that. And this is known this is not a classical model, but this was introduced by Moshe Neuberger and Shapiro. It was introduced in 94, sorry, 94 in the context more in the context of quantum chaos. I should mention here that this RMT model, I will come back to that, but yeah, several people tried to study this model at finite temperature, and in particular, rather recently, Dong Wang and Carl Yeshti tried to look at this model at finite T. This also was studied by Kurt Johansen in 2007, sorry, I will mention this a bit later. So this is a first remark, is that there is an RMT model associated to that. And this is a nice remark, I would say. There is another remark which is less pleasant. It turns out that this model is not determinantal anymore. And that means that you lose the determinantal properties. In particular, you can check, for instance, that the kernel, that the kernel that you can construct is not reproducible, and eventually you fail. You can show that it's not a determinantal point process. Okay, so that's quite bad, because you can't use anymore the techniques that we like from determinantal point process, but this point process is not determinantal anymore. So in principle, indeed, that means that the effect of temperature are quite nasty, and that breaks this nice structure, the nice tools, that nice toolbox that we have. Now, fortunately, and as it has appeared in other models in probability or in combinatorics, you see here the difficulty actually comes from the fact that we are working with a finite number of particles. Okay, so that's in the canonical ensemble, and that's the that would be somehow, it's called canonical also because the this is a sort of natural way of looking at the system from a statistical mechanics point of view. But in the canonical ensemble, the number of particles n is kept fixed, and that actually creates some complication. Now, it's well known that, for instance, if you think about the longest increasing subsequence, or say the Hammersley problem. Okay, sorry, I'm just taking one question. So, was the previous expression not just a single determinant Cauchy-Binet? Yes, that is true. Yeah, you're right. Yes, that is true. But it doesn't help really now if you want to. Yes, that's true. But if you want then to compute correlation functions and so on, okay, that's so if you want to integrate, if you want to compute marginals, then you are in trouble. But yes, you're right. This is a determinant, and basically this will be the determinant of a kernel, but this kernel eventually is not reproducible.
Thanks.
Okay, yeah. So that's the problem. The reproducibility is actually the problem. Okay. Now, as I said, in many other problems that we know, like the longest increasing subsequence or the Hammersley path process, it's sometimes more, or say easier, more convenient to consider that n is a random variable and look at a kind of, for instance, Poissonized version of your model. Okay? And in this case, and that's the case, for instance, of the longest increasing subsequence, the Baik-Dave-Johansen paper basically deals with the Poissonized version of the longest increasing subsequence. So here, the same thing actually happens in the sense that it turns out to be more convenient to make this n random. And in statistical mechanics, there is a canonical way, or a standard way, I should say, to do that, is to work, instead of working in a canonical ensemble, is to work in what is called the grand canonical ensemble. Okay. So where basically n is now a random variable. Okay, so in this case, it turns out that the grand canonical ensemble, so that means that the Pn, there is now a probability Pn for a given number of particles, and it has a certain expression which I write it explicitly for you. I will not do so much out of it. I'm sure, I mean, Jeremy will discuss this from a slightly different perspective. And basically, this is written this way. So Zn is what I said before. So it resembles a kind of Poisson distribution, but not quite because of the Zn. And Z mu is just the normalization factor. And mu is called what is called the chemical potential in statistical mechanics. Okay, so this mu here. Now the great thing is that in the grand canonical ensemble, okay, so that's this ensemble here, right? Grand canonical ensemble. Now the process becomes determinantal again, and then of course you are quite happy because you can use all the machinery that you have from the DPP, from determinantal point processes. Okay, so that's the really the point. So again, you might think of it as a kind of Poissonized version of your model, but in a grand canonical ensemble, the point process
Sorry, there was a question.
Oh, sorry. Yeah, I missed it.
What is Z of mu?
Yeah, Z of mu is just a normalization. It's just a normalization constant. I didn't want to write it explicitly, but this is just the sum over n from 0 to infinity, or 1 to infinity of this weight here. Is that fine? Yeah, it exists. I mean, okay. Thank you, Mattia. So this point process becomes determinant. And on top of that, I mean, the kernel, in fact, has a very explicit expression. So it's now indexed by mu instead of n. And this is, again, expressed as a sum over all your eigenstates, phi k star of x, phi k of y, but now there is a factor that ponders this, which is well known by physicists. Okay, so that's the expression that we get. Okay, so that's this guy. And what is sort of, again, from the physics point of view, this factor here is just what is called the Fermi factor. And that simply tells you the average number of fermions that occupy the level with energy epsilon k. Now, again, if you just look at the beta goes to infinity limit, so the zero temperature limit, well, what will happen is that this Fermi factor here is just a kind of step function, and it really cuts the sum here at epsilon k equals mu. Okay. And mu essentially is the last, is the energy of the lastly occupied level. And you get back the expression, the standard expression for the kernel that we had at 0 temperature, which basically was this one. Okay. So yeah, this allows to see that I made a mistake here. I mean, I started to label the level from k equals to 1. Okay. Now, of course, So that means that eventually we will be able to compute things there. Now the question, which is to some extent in this problem still open, at least from the mathematical point of view, is how to relate the two ensembles. Okay, so the ensembles, the grand canonical ensemble where mu is fixed, and the canonical ensemble where n is fixed. Now, usually, what we expect in classical, in standard, I should say, statistical mechanics is that in the large n limit, the two ensembles actually coincide. At least if you look at the local correlations. And the argument goes as follows: is that typically what happens is that, although in this case, in the grand canonical ensemble, so mu will be typically quite large. But essentially what happens is that n is a random variable now. Okay, so the number of fermions that you have in your system is a random variable, but it turns out that the fluctuations of these guys, of the number of particles around its mean value is very small. And eventually that means that the system basically behaves as if the number of particles were essentially fixed with very small fluctuations around its mean. And the mean of the particles that you have inside your system is basically completely controlled by n. So the claim is, but this is not a proof, but the claim is that, and as far as I know, there is no proof of that. I know that Kurt Johansson, I've thought a lot about this problem. But the claim is that basically, the canonical ensemble is sort of equivalent to the grand canonical ensemble. So here again, we have n. This is n is fixed, mu is fixed, and the relation is just that basically n. So the mean number of fermions in the grand canonical ensemble is exactly given by n. Okay, so the relation between the two quantities is just that mu. Sorry, n is just the mean number of fermions, and the mean number of fermions in the grand canonical ensemble is simply given by that. So what I want to claim eventually is that even though in the canonical ensemble, the system is not determinantal, it becomes so in the large n limit where the system is equivalent to the grand canonical ensemble. And that should be true at least at the level of local correlations. But there is no proof of that again. Okay. Still, you can do progress because you can say, okay, let's just forget about this equivalence if you don't like it. But at least I can study things and say what happens in the grand canonical ensemble because I have a determinantal point process, and therefore I can actually do computations there. And I want to study what happens in the large mu limit, which is equivalent to the large n limit. Okay, so I want to be able to study some kind of local what happens in the large mu limit, and what will, for instance, what is the fate of the Henry kernel at finite temperature? Okay, is there what is it? What is its expression? I mean, how does it look like? How is it modified by temperature? So before doing so, I just would like to end up, or to discuss a little bit the physics of what happens at zero temperature, at finite temperature, sorry. And I would like to understand what happens and what are the relevant length scales at finite temperature, and try to understand how the temperature will affect both the bulk and the edge. So to do that, I just, so that's, so remember that at t equals 0, we had two length scales, the bulk and the edge. So that's typically the interparticle distance, both in the bulk and at the edge. Now, as soon as you are at finite temperature, if you want, the temperature itself sets a new length scale in the problem, and this new length scale is called the de Broglie wavelength. Which I want to call lambda t. Now, what is the physical meaning of this lambda t? Well, basically, lambda t corresponds to the spatial extension of a certain state, which is at equilibrium at finite temperature, t, and that represents the typical extension of its wave function. Okay, so that means that if I look at the wave function of one particle, basically it will have some width. It's a physical argument, right? It's just to get you the idea of how to understand what happens. So this is just a single particle. So this is a single particle. PDF. Well, it will have a kind of bell shape form, whatever. And what lambda t is basically the typical extension of this guy at finite temperature, provided the particle is at equilibrium at finite temperature. And you can estimate this lambda t, and this is what is called under the name of the de Broglie wavelength. This is just given by h, the Planck constant. So I give you all the factor here, by 2 pi m kBt. Okay. So basically what you understand is that in particular, of course, when t is very large, then lambda t becomes very small. So that means that lambda t then in this case, I mean, the psi of x squared becomes almost a delta function, okay? So this lambda t, you see, controls the importance of quantum effects. Now, of course, this lambda t has to be compared with the typical distance between two particles, okay? Because if lambda t is much larger than the interparticle distance, then you would expect that quantum effects will be important. On the other hand, if lambda t is very small and much smaller than the interparticle distance, then you would expect that quantum effects will be unimportant, and basically only what will matter are only the thermal effects, and somehow you will lose completely the effects of Pauli exclusion principle and quantum mechanics. So you see that depending on the bulk or the edge, because the scaling, of course, is quite different, well, you see that there is a temperature scale, which is quite different, both in the bulk and at the edge. So if you want this lambda t, as I said, this controls the crossover between quantum to classical behavior. Sorry, controls D. Crossover from quantum to classical behavior. Okay, so let's look at what happens is that if you are in the bulk, well, the crossover happens when lambda t is of the order of the interparticle distance. So that means 1 over square root of t is of order of 1 over square root of n. So that means t of order n. While if you are at the edge, of course, it's much more sensitive, okay? Because the density is also smaller, the system is much more sensitive to quantum fluctuations. And in this case, you see that if you just equate 1 over square root of t with 1 over n to the power 1/6, then you see that the crossover scale is actually at t of the order n to the 1/3. So this is quite nice because that means that if you, so in other words, you can actually perturb what happens at the edge without touching too much what happens in the bulk. And in particular, that means that if you are at t of order n to the 1/3, then you would expect to see a nice crossover, if you want, from purely quantum to thermal behavior. But the global behavior, so that means that if you look at the density, basically you will still see the Wigner semicircle, but the only thing that you will modify is what happens at the edge. So in other words, if you look at, and in particular, say, if you look at what happens for the distribution of the rightmost particle at the edge, then you will see that things becomes different, provided you have scaled your temperature correctly. That means that t is over the order 1/3. So that's, I will just end up with that, and I will just then, so let me just say what happens at the edge. So in other words, maybe I need to, I still have 5 minutes, right? Is that fine? I mean, or, okay.
Next talk is at half hour, so
okay,
there's still time.
Okay, good. So again, if I look at the density, so if I set, say, a temperature T, which I will denote by, say, 1 over B, so that will be my control parameter. So I will set T equal to 1/3. T to the power 1/3. Okay. So what will happen is that the bulk will be untouched. Okay. So, but only the bulk is perturbed. And I would like to understand what happens in the bulk. So what I'm saying is that at the edge, sorry, so bulk is unchanged. But I want to understand what happens at the edge. Okay, so that means that if I look at that, so in the limit B goes to infinity, I should recover basically the 0 temperature limit, while when B goes to 0, that would correspond to a high temperature limit. Okay, so 1 over B is like the rescaled inverse temperature. So the interesting stuff, indeed, the interesting property is indeed what happens if you look at the rightmost fermion. So let me just end up with that. Right, probably. So I will denote now its position x max of t. And I want to write, so okay, I want to understand what happens in the limit when n goes to infinity. So let me just scale the things as what one should scale them. So we know that we should look at what happens close to square root of 2n, because the support of the Wigner semicircle will not be touched. And I need to look at fluctuations, which are, as we know, are of the order of n to the power minus 1/6. Okay, there is a square root of 2 factor, which is introduced hereby for convenience. And this actually is So this is what we showed, and similar result actually had appeared before, for instance, in particular by Kurt Johansson. But so PS, I already said what it was. It's just a projector on S plus infinity. So I don't want to discuss so much this guy, but I want to write explicitly what this KB is. So it depends continuously on this parameter B here. Sorry, this guy. And let me just write it explicitly. It's a kind of modified area kernel and deformed by temperature, if you want. So it's a sum of these guys, which we know. Sorry, so this is it has two arguments. And this should be so this is very similar to what we have seen before at zero temperature, but now of course we have this Fermi factor, okay, which is of course reminiscent of what you had in this formula, which is basically this guy, okay. So this is the scaling limit of this guy. So that's quite nice. In fact, this has been derived by many people in various contexts. This has been studied by many of you. I mean, there are many people here. I just see the name of Alexandre. I mean, you will say more on that, I suppose, in his talks, and more complicated generalization of this. I should probably mention, not probably, I should mention Tomohiro also, Mattia, and some others that I probably don't see. One thing that we pointed out, but okay, I will not have time to discuss this now. Maybe if I have time later on, I could say a bit more. But quite remarkably, I mean, what we noticed with my colleagues, Satya Majumdar, Pierre Ledoussal, and David Dean, is that this kernel here, in fact, appears in the context, which is not completely related, but not unrelated to this, which is the KPZ equation at finite time. So, and that's still kind of mystery as to why this kernel appears there.
This looks like the same deformation, but in the KPZ,
yeah,
there is a 1 minus exponent.
Yeah, but actually, I mean, if you really rewrite it, so yeah, indeed, it looks like a Bose factor. But in fact, if you look at not the PDF, but the generating function of the PDF, then it actually you really, there is a kind of duality between bosons and fermions in this formula, which is a bit indeed. I mean, at least.
So you can get the KPZ narrow
yeah,
wedge
exactly.
distribution.
Yes, exactly. Maybe I can just, if I have a few minutes, I can just show it to you. Okay, so the way it appears in KPZ is the following. Yeah, sorry, I will scroll it. But okay, so for KPZ, I will not introduce KPZ for you. I'm sure you know this very well. But so the quantity that you need to look at, can you see it? So yes. This is this generating function actually. Okay, so so instead of h is the standard height in the KPZ. So now you look at exponential of h, which is essentially the partition function of your polymer in the language of the directed polymer, and basically you look at this the generating function of this partition function. So it's not directly the PDF indeed, but this guy has exactly this expression. And indeed, here you have the plus sign. But you are right that if at the end of the day, if you really want to compute the PDF, eventually this plus sign by some miracles will transform into a minus, so a bosonic factor. But yeah, so that's basically it then. So that's what I wanted to say. So okay, so that was a quick panorama. I mean, of a quick overview of one of the simplest case where one can try to understand the effects of temperature in a non-trivial way on non-interacting fermions. This, of course, so there is actually one question that you may ask is that we know that for Tracy rhythm, there are actually associated Pain-Levé equations. And so there are generalization, non-local generalization of this Pain-Levé equation for this problem, which was actually obtained by Corwin, Castell, and collaborators. And this has been extended recently by Alexandre and his collaborators and other people too, to more complicated problems, namely these multi-critical cases, which maybe you will discuss, Alex. So okay, so I will end up here. So yeah, and of course you will have a complementary view on this from the different perspective in Jeremy's talk on Thursday.